Hello, and welcome to our lecture series for Chapter 3, which is about chemical bonding. I want to begin by talking about the last section of the chapter, which is section 3-12, in which we name simple compounds, very simple compounds, usually with only two elements as part of their composition. Before we do that, I want to clarify the difference between the two major types of chemical compounds that there are: ionic compounds versus covalent compounds. It's very easy to tell the difference between ionic and covalent compounds. Ionic compounds are always going to be compounds that contain a cation and an anion bonded together through an ionic bond. Cations are always going to be metals, and anions are going to be nonmetals. So if you see a compound in which you have a metal along with a nonmetal, you know that's going to be an ionic compound. Covalent compounds, which are also known as molecules or molecular compounds, okay, this is synonymous, those have atoms that are bonded together through covalent bonds that share electrons. And these always involve bonds between nonmetal atoms. So if you see a compound that only contains nonmetals, that's giving you the clue that it's a covalent compound, also known as a molecule. So I want to start off today by talking about naming simple compounds. And the first type of compound that I want us to name is known as the binary ionic compounds. Like the name implies, binary means two. So these contain two elements, one cation. I'm going to make that more specific by saying one metal cation plus one nonmetal anion. Very simple. So if you see a compound made up of two different elements, one of them is a metal, one of them is a nonmetal, you know it's a binary ionic compound. Now, in order to name binary ionic compounds, first we have to look to the periodic table, and here you have to start being able to correlate names with symbols. So I want to go through this table quickly, just the first four rows. And what I would like you to do is, as I call out the names, I would like you to repeat them after me, because I want you to start to get fluent in the language of the periodic table, the language of chemistry. So repeat after me: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, and krypton. So, as you may have noticed, most of the names kind of correspond to the elemental symbols, like B is boron, C is carbon, N is nitrogen. But some of the names really don't. So the odd ones come from Latin roots. For example, Fe. Where does Fe come from? In English, we call that iron, but it comes from the Latin word, which is ferrum. So that symbol comes from the Latin root. What else can we say? A few other names that you might want to know. For example, silver and gold. Those also come from Latin roots. You'll notice a lot of the metals have names that are of Latin origin. So Ag is silver, and that comes from the Latin argentum, like money. Au is gold, and that comes from the Latin aurum. What else has a Latin root? Pb is a good example of an element with a Latin root. Pb is lead, like lead pipes, and that comes from the Latin plumbum, like plumber, lead pipes. So you can see that a lot of the symbols, particularly for the metals, come from Latin roots. So it's important that you know the which elements correspond to which names. Potassium is K. The Latin root there is calcium. Sodium is Na from natrium, etc., etc. Okay, so you have to know the names of the different elements in order to name binary ionic compounds. Um, Now, the way that you name them, this is binary ionic compounds, is that you name the cation first, just by naming the element. Then you name the anion. So the anion gets named last, and you change the ending so that it has an "ide" suffix. Let me show you a couple of examples of what I mean. You already know some examples. NaCl is a famous one. So you just name the Na, which is sodium, and then Cl is chlorine, but you change the ending. So instead of chlorine, you make it into chloride. Let me give you another example. KBr, another binary ionic compound. K is potassium, so we simply name the cation. And Br is bromine, but again, we change the ending, so it's bromide. LiH. Lithium is just lithium, the element's name, the cation. And the H is hydride. So H is, of course, hydrogen, but you change the ending so that it's an "ide" suffix. So the ratio of atoms in all of these are such that it's a 1-to-1 ratio. The charges are balanced to make neutral compounds, but sometimes you don't see that. For example, Al2O3. Aluminum tends to take the +3 charge, and oxygen tends to take -2. So we need them in a ratio of 2 aluminums to 3 oxygens to get a neutral compound. And that means that when we name it, we actually just ignore the numbers because the numbers don't matter. The charges are always the same. So we just call this one aluminum oxide. The same would go for, let me think of another example. Let's try K3P. 3 potassiums for every 1 phosphorus. But all we do is just look at which elements are involved. So this one would be potassium phosphide. So we take phosphorus and we change the ending to "ide." Now, your book has a very useful table, table 3.5, showing the common monoatomic cations and anions that go into binary ionic compounds. So here are the cations. We have hydrogen, lithium, sodium, potassium, cesium, beryllium, magnesium, calcium, barium, and aluminum. Now you'll notice that most of these are in group 1. So that is, of course, the alkalis, and they have +1 charges in compounds. Then all of these are in the group 2, the alkaline earth metals. Those all have +2 charges on the ion. And finally, aluminum is in group 13, and that always takes a 3+ charge. So you see these cations very frequently, and they always take the same charges. That's why we don't need to specify the number of atoms in the elements and the compound's names. Now, the common anions are listed here. These are the nonmetals. So hydrogen can kind of go both ways. It can function as a metal or a nonmetal. In fact, it's usually classified as a nonmetal. The hydrogen would be hydride, fluoride, chloride, bromide, iodide, oxide, sulfide, nitride, phosphide. Notice that the names of these have been altered to give them an "ide" suffix. Now, hydrogen and all of the halogens would take a -1 charge on their ions in compounds, whereas oxygen and sulfur, being in group 16, those would take a -2 charge on their ions. And nitrogen and phosphorus, being in group 15, would take a -3 charge because all of these are going for the noble gas configuration. So they tend to gain electrons to make them have a noble gas configuration. So this has consequences. One thing that you guys are going to have to do is not only go from the formula to the name, but vice versa, from the name to the formula. So that can get just a little bit tricky when you go in the opposite direction from the name to the formula. Let me give you an example of this. Can you write a formula for the following compounds? So I'm going to give you aluminum bromide, calcium oxide, barium fluoride. Okay, so writing formulas from the names is just a tad bit more tricky. Here you really need to know which ions each element forms. So aluminum forms the 3+ ion in compounds. We kind of see that in this table. You can also see that in the periodic table. Bromide refers to Br-1. Now, when these come together to form a neutral compound, you are going to need 3 bromines to have a 3- charge to balance out the 3+ on aluminum. So that means that the formula of the resulting compound is going to be AlBr3. A kind of little shortcut to help you do that is to bring the absolute value of the ion's charge down to become kind of the opposite subscript. So we see that the 3 comes down to make the subscript here. Let's do the same for calcium oxide. Calcium is an alkaline earth element, so it's going to be Ca2+. Oxygen is in group 16, so it's O2-. Now, when those come together, notice their charges are equal in magnitude. 2+ and 2- cancel each other out. So those will come together in a 1-to-1 ratio. You should always use the lowest whole number ratio of elements in the compound, in the ionic compounds. Okay, so we don't want Ca2O2. You want to reduce it to the lowest whole number ratio. Okay, so lowest whole number ratio of elements to each other. Finally, barium fluoride. Barium would be Ba2+ because it's an alkaline earth element. Fluoride is F-1. So when those come together, we need 2 fluorines to balance out the barium. Another way of saying that is we bring the absolute values of the charges down. And there you can see that we need BaF2. So you really need to use the charges that the ions tend to take in order to figure out what the formulas would be for the names of binary ionic compounds.